Hello. Today we're going to talk about the ideal gas law and how the ideal gas law came about and what assumptions we have to make in order for a gas to be ideal, and what does ideal mean. Okay, so last time we talked about the combination gas law, right? And it was pressure times volume over a temperature. Okay, and that is equal to some, we'll call K, some constant. All right, and that's also derived from Boyle's law, which again is a constant if the number of particles and the temperature are held constant. And then we had Charles's law, also equal to a constant. Again, that is true as long as the number of particles and the number of moles and the pressure is held constant. Then we get to Lusak's law, and we find that pressure and temperature are related, okay, with a constant, and you guessed it, as long as the number of particles and the volume is held constant. Okay, now, and the combination gas law gets derived from these three laws: Boyle's, Charles, and Lusak's law. Now, and guess, the only thing that makes this work, and if you can guess, well, what has to be held constant? Obviously, pressure, volume, temperature, all changing. So the thing that is held constant is the number of moles. So what happens when the number of moles are not held constant? Okay, that gets related to something called Avogadro's law. All right, and Avogadro's law says that the number of the volume of a gas will increase as the number of moles increases. Again, that is equal to some constant. Okay, so how do we fit this in to the combination gas law? Well, since it's in the denominator, we are going to put it down here. All right, and again, this is when that's not held constant. Okay, when pressure and volume and moles and temperature are not held constant, they are equal to what we call R, which is, believe it or not, a constant onto itself. So we have PV and the number of moles and temperature. It'll always equal a certain number. Now, this number will only change if depending on whatever units of pressure. So, since this is always going to be a constant, and we don't want an equation with variables, usually in the denominator, we want to rearrange this. Multiply both sides by n and t. We get n and t go bye-bye. We get PV equals RTN. Now, you don't usually see it like this. You see it as PV equals N RT. Pressure times volume equals the number of moles times a constant times its temperature in Kelvin. Okay, so we're going to be working with this equation and the derivations of this equation. To basically find out, we can solve for P and PV and R. Okay, I'm sorry, not RT. So again, R is a constant. We'll talk more about R in 1 second. So, some things we have to make assumptions, okay? So what makes a gas ideal? Two important assumptions we have to make about kinetic molecular theory. is that gases do not occupy much space, or they do not attract one another. And if they don't attract one another, all right, they will not lose energy to one another. And these assumptions work very well when you are at relatively low pressures and high temperatures. If we start to get at relatively high pressures and low temperatures, that makes a gas more real. All right, and we'll show you how to deal with that on a later date. If you are taking an AP course, this right here, right, you will always see somewhere on the multiple choice section of an AP test, guaranteed 100%. So these are the two important things that we have to realize when dealing with a gas and making it ideal. We don't want any interactions between other gas molecules or the walls of the container. Okay, and that works well when we're at low pressure and high temperature. All right, so let's talk about R. Okay, we said R is a constant. Get another little piece of paper over here. All right, so we have PV equals N RT. Now, PV, R, and T are uppercase letters, and N is a lowercase letter, and that has to deal with something called a state function. Okay, so we'll deal with what state functions are on a little later date, but for right now you really have to know that. If you want to go look up what a state function is, you're more than welcome to. But in order to solve these problems, we don't need to know that. Okay, so if we want to solve for R, okay, so we would divide both sides by N and T, and that would give me PV over N divided by T. Now, pressure, it all depends upon what unit we're talking about. All right, so the most common one would be ATMs. So if my unit's in ATMs, my volume has to be in liters for ideal gas law, divided by MOL for moles, times the Kelvin temperature. So this is actually the actual unit for R. Okay, I know it's a big crazy unit. Now the physical number will depend upon what that unit of pressure is. For ATMs, it happens to be 0.0821 atmospheres times liters times mole per Kelvin. All right. If you're dealing with kilopascals, okay, we just change that pressure unit to kPa, and that's equal to 8.314. And these are R values. If I'm using kilopascals, if I'm using millimeters of mercury or torr, okay, the number changes again. All right, so that is equal to 62.4 millimeters of mercury, or you could also use torr for this because they're basically the same unit. All right, so these are the three values of R that you'll see the most. All right, you do see once in a while you'll see pascals, but that's really, really rare. All right, but these are the ones for the courses that we're taking we're going to focus on. Okay, so let me show you what this actually looks like. Let's do a couple problems. All right, we'll run through a couple of examples, and then we'll talk about the derivations of the ideal gas law. Okay. So, here's an example. How many moles of air are there in a 2-liter bottle at 19 degrees Celsius and 95.3 kPa? So, if you want to use the ideal gas law, hit the pause button and try to solve this. Okay, so let's see what we got here. So we're using the ideal gas law. PV equals nRT. Okay, so what I like to do is I like to solve for the unit that I am solve for the constant I'm trying to solve for. So in this case, we are solving for the moles, which would be N. So if we divide both sides by RT, RT goes bye-bye here, and we have N equals PV over RT. All right. Now again, when you are actually doing the math, make sure that you multiply those two numbers first before you divide them, or put them in parentheses in your calculator, or your calculator will just multiply PV, divide by R, and then remultiply it by T, which we don't want. All right, so let's see what we got. We have a pressure, and that is pressure is in kilopascals, and that's important because that's going to determine what R we're going to use. In this case, the R value would be 101.3. Oh, sorry, not 101.3. I'm thinking about the standard pressure for kilopascals. It would be 8.314. Okay, so the R value that we're going to use here is 8.314. Again, the units would be kPa times liters, mole times Kelvin. And you're going to see how important that is in a second when we plug this all in. So, plugging this in, okay, the pressure we have as 95.3 kPa times V, which is 2 liters, over R. All right, since we're using a kPa value, we got to use 8.314 kPa times liters over mole K. And yes, you got to put it in. All right, it's not my rule, it's how it works. And the temperature, well, now we can't use Celsius because this is not in Celsius, so we got to take our 19 degrees and add 273.15. all right, and that would give us no places behind the decimal. All right, and I believe that comes out to be 292 Kelvin. So we plug in 292 Kelvin here. All right, and look what happens. kPa cancels out, liters would cancel out, kelvins would cancel out, and we're left with the unit that we're looking for, which is moles. So if we did this right, you should got point, I believe, 0.78 5109 and a bunch of other things. So again, we are bound by the laws of significant figures. So we have 3 here, 2 here, 3 here. Now R is a constant, so we don't take sig figs from that. So lo and behold, we should have 0.79 moles as our answer. All right. Okay. So let's try one more, and then we'll talk about the derivations of the ideal gas law. All right. So we have another kPa problem. So what is the kPa pressure exerted by 1.80 grams of hydrogen gas? Again, hydrogen is a diatomic gas. In a 4.3 liter balloon at 27 degrees Celsius. All right, so right off the bat, I want to write my PV equals nRT. In this case, we are solving for pressure. So pressure dividing both sides by V, I think you figured that out by now. P equals nRT divided by V. Okay. So we have to do a couple conversions here because we're in grams and we got to convert that to moles. Okay. So if I have 0.180 grams of diatomic hydrogen, all right, so again, we should understand that to go from grams into moles, okay, we divide by the molar mass. I'm going to use 101.1 just to make things simpler for right now. All right, and that should give us, I believe, 0.891 moles of H2 at 3 sig figs. And then we got to take this and convert that to Kelvin. We have to add 273.15. This comes out to be, I believe, 300.15, but again, that has one spot behind a decimal, this has two, so it would be 300.2 Kelvin. Alright, so now we're ready to plug into our equation over here. So pressure, and we have the number of moles, which we said is 0.819 moles. We have R, again we're using kPa, so R is 8.314. Again, kPa times liters times mole times Kelvin, times the temperature in Kelvin of 302.2 Kelvin. Alright, multiply all that out, and then we go and divide by the volume, which is already in liters for us, which is nice. Okay, here we're this has 3 sig figs. That's a constant, we don't care. This has 4, that has 3. So our pressure should be 517 kPa. Alright, well, hopefully you got that. Alright, so just going to talk about for a couple minutes some derivations, some other questions you might see off the ideal gas law. Now, when we convert, since we're dealing with moles, when we convert from grams to moles, we essentially taking that mass of whatever that is in grams, and we are dividing it by the molar mass. So that's always going to equal the number of moles, or N. Alright, so if we take PV equals nRT, okay, we can substitute G over mm RT for where N is. And then you can go and you can solve for the molar mass of a gas. Okay, if we multiply both sides by mm, which is the molar mass again, it leaves. Okay, and then we have mm times PV equals G RT. Alright, well, again, we got to get rid of PV, so we divide both sides by PV. And we get the equation: the molar mass of a gas is equal to G times R times T. Now, divided by PV. I'm just going to flip these here for a second. Okay, instead of saying PV, I can, since they are a distributive property, I could say VP instead. Now, if you notice, I did that for a reason. Okay, grams divided by a volume. All right, you're going to have to think back a minute. What does grams divided by a volume represent? All right, you're all trying to scratch your head. I'll give you a hint. It begins with D. Yes, density. Remember? Density is a mass unit divided by a volume. Okay, now, most of the times we're talk about a solid or a liquid, we look, S means solid, L means liquid. We certainly use those units for solids and liquids. But for gases, okay, especially dealing with the ideal gas law, okay, what volume does the ideal gas law always have to be in? All right, has to be in liters. So the density for a gas is always going to be grams per liter. Okay, and we can substitute even further. We could say density times R times the Kelvin temperature divided by, oops, I'm running out of space here, pressure. All right, and then you could further take this and solve for density if they're asking you to solve for density of a gas. Okay, and they're giving you the molar mass and they're giving you the temperature and the pressure. So you can certainly, most certainly do that, and on the worksheet you'll see that. Okay, so ideal gas law, again, we're talking about when pressure, volume, temperature, and the number of moles are not constant. Okay, or rather changing, and they are changing, they have to equal one of those gas constants that we talked about. Okay, and that is essentially the ideal gas law. All right, if you have any questions, email me. Next we'll be looking at gas stoichiometry. See you soon.